if I want to calculate the bond energies in this particular equation over here, first thing that you need to do is you need to actually draw out the different molecules. Now, you're already expected to know that what water looks like, what carbon dioxide looks like. So water is going to be an angular molecule, carbon dioxide is going to be a linear molecule, oxygen is a diatomic linear molecule. You're not yet expected to know what C2H6 is. So we've drawn a picture for you on the side over here of that molecule, and when you unpack it, you can clearly see two large grey dots and six smaller white dots. So that's obviously representing the carbons and the hydrogens. You can see one stick between everything, and that means that it's just a single bond, single bond, single bond, single bond, single bond, single bond. Does it make sense? Well, let's see. Carbon's supposed to have a valency of 4. So yes, it links onto 4 different things, and it links onto 4 different things. And hydrogen's got a valency of 1, so it's going to link on just once. And so it all makes sense. Use the bond energies given in the table and the diagram of ethane to calculate the energy changes for this reaction. Show all your working. So the first thing that we're going to do is we're going to say, all right, well, I've clearly got 1, 2, 3, 4, 5, 6 carbon bonding to hydrogen. So 6 carbon hydrogen bonds. So that's 6 times 415. That's equal to 2,490. I have also got 1 carbon-carbon bond. So I look for the carbon-carbon bond energy that I've been given, and it is 350. Add it on, and I find that it's 2,840. But according to the balanced chemical equation, I've actually got 2 of those, so I mustn't lose sight of that when I'm doing my full calculation. Multiply that by 2, and I land up with 5,680 kilojoules of energy will need to be added to break bonds. So this is energy added. That's not the only energy added. The other energy added is going to be over here, where I am going to have to break 1 double bond oxygen. So double bond oxygen is 500 over there. How many oxygens do I have? I have 7 of them. So 7 times 500, and I get 3,500. Remember, breaking bonds always requires energy to be added. Now we're going to make some bonds. So I go over here and I see that I've got 1 carbon oxygen, 2 carbon oxygens with double bonds, and I see that those come in at 799. So it's 2 times 799. And I'm going to have to multiply that whole thing by, there's a 4 in front over there, times by 4, and in total that's going to come out to be 6,392. Taking a look at the water, I have to break 2 oxygen hydrogens. Oxygen, hydrogen, 460. So it's 2 times 460. And how many are there in the equation? There are 6 of those. So that in total works out to be 5,520. This is the energy that is going to be released. Okay, so if I add all the energy that's going to be released, so I add the 6,392 and the 5,520, I find that I get 1,1912. If I add all the energy that is going to be added, I'm adding 5,680 and I'm adding 3,500. I find that my total amount of energy that I had to put in was 9,180. Clearly, I have released more energy than I have put in. Subtract the 2 from one another. 11912 minus 9180 is going to be equal to 2,732 kilojoules released. State with a reason whether this reaction is endothermic or exothermic. Because the energy is being released, this is an exothermic reaction. More energy is released than the amount of energy that has been added into the reaction. Draw a fully labeled energy profile, including values for this particular reaction. So, what are we going to do? We need to give ourselves an X and a Y axis. This is called your reaction coordinate. Your y-axis is going to be your potential energy. And you are going to draw the classic exothermic curve. But it does ask you to also put some values in. So let's think about that. How much energy did I need to put in? I needed from these, remember, that's my reactants, that's my products. So from reactants to the activated complex, I added 9,180 kilojoules. From the activated complex down to where the products are made, I have released, they tell me the total amount of energy released is 11,912. Got that from there. So 11,912 has come in as the energy released. The energy put in is the 9,180 over here. Energy put in. And finally, I need to say what was the net energy change. So my net energy change was the 2,732. 2,732. I've now labeled that diagram with values.